So in this section of logic, we're going to discuss truth tables. We're going to look at tautologies and contradiction. We're also going to look at logical equivalence. And then on top of that, we're going to discuss contrapositive statement, converses, inverses, and then we're going to do necessary and sufficient conditions. So 6 is out. We're just going to do 1 up to 5. All right. Let's start with truth tables. So let me do this first one. So let's do it step by step together. Let's say construct a truth table for the propositional formula. So P or Q and not P and Q. So as usual, you use a formula 2 to the power n, where n stands for the number of variables. So 2 to the power n, there's only 2 variables, P and Q. It means you're going to have 4 possible combinations. All right. And we go in that order. P, you need a column for Q. And we need, because there's only 4 combinations, so I need 2 truths, 2 false. And then I have to have that value there. So I get 1 true, 1 false, 1 true, 1 false. All right. In that order. Now, the first 2 columns is a given, meaning that I expect everyone to be able to get the first 2 columns right. All right. So most of the mark will be awarded for what comes next. All right. So P or Q, obviously true or true is true. Remember, when we talk of disjunction, you just need one of them to be true for the outcome to be true. So true or true is obviously true. True or false is true. False or true is true, and false or false is false. And then for conjunction, you need both of them to be true for the outcome to be true. So you only get true when you have true or true. So when you have P is true and Q is true. Everywhere else you see here, we just get false, false, false. All right. And if you notice it, there's an order in which I represent this things on the table. So what I use is, I use the idea of BODMAS followed by the precedence. So the order in which this connectives are used. For example, I start with brackets. So I focus on the bracket. I'm moving from left to right. So after listing these first 2 columns, you move from left to right using BODMAS. So I start with the first bracket, P or Q. That's the reason why you see here we have P or Q. Once I'm done with P or Q, I move to the next bracket. So the next bracket there is P and Q. You can see they have P and Q. And we're not done. There's a negation there. So you also need to do that. So you see there, I have the negation of P and Q. And then finally I have the whole thing now. All right. There we go. And if you do it in that order, it becomes easy for me to mark. I'm not saying this is the only way you can do it, but if you do it this way, it becomes easy for me to mark. All right. But very important, always check to make sure that what you get here is correct. All right. If everyone is happy with this example, let's look at example 2, where they ask us to construct another truth table. All right, example 2 is a much bigger table. So let's see, now you have 3 variables. Again, you use the same formula, 2 to the power numbers of variables, which is equals to 8. So you have 8 possible combinations. Now for 8 possible combinations, the first 3 columns, like I said, everyone should be comfortable with that. You have P, Q, and R, all right? And how does it work? Because I have 8 combinations, it means I'll start by saying 4 truths, 4 false. When I go to the next variable, which is Q, in that order, remember we start with that variable P, we go to the next variable Q, and then we go to R in that order. Now for Q, I'll have this statement. So I'll now have 2 truths, 2 false, 2 truths, 2 false, all right? Just to be consistent. I'm not saying that this is exactly how it's supposed to be, but just for you to make your work very consistent. And it makes my life easy when I'm marking. And then for arrow, again, you have those options there for Q. So you're going to have 1 true, 1 false, 1 true, 1 false. All right. So for your last variable, notice it will always be 1 true, 1 false, 1 true, 1 false. All right. Now, again, we need to apply BODMAS moving from left to right. So if you look at BODMAS, I say you start with the innermost bracket. So we're going to focus on that one inside there. inside there, notice that there is a not Q. So we start by dealing with that negation inside that bracket. So I start with, I deal with not Q, and then I can do the whole bracket, which is P and not Q. After doing that, then I do this outer bracket, now this big one that you see here, this big bracket here, which is P and not Q or R. And then going to the right, you can see that I have a not R. That's why we have a not R there. And then I'm done. Then I have the whole thing. All right. I'll just do the first line. So obviously, if Q is true, not Q, there will just be false. Let me just change the color. So not true, there will is false. P and not Q. So it means you're going to have true and false. Remember, and both of them needs to be true for it to be true, means your outcome again will be false. And then you need to take this whole result here and you say or R. Remember, R there is true. The fact that R is true, you have false or true, it becomes true. All right. And then not R. So if R there is true, so take note R here is true. Not true just becomes false. And then if you take true implies false. So if you notice it, this whole thing here is now implied not R. All right. So it becomes true implies false. So a statement that is true cannot imply another statement that's false. So your outcome there is just right. So repeat that same process for all of us and make sure that you check. Sometimes the way we choose to test you on this is I actually give you the truth table that I can choose to take out some of those guys, all right? And you should be able to fill in the missing truth values, all right? So the two ways of doing it, construct the truth table from scratch, or I give you a truth table and I say fill in the missing truth values, all right? I hope everyone is happy. Okay, looks like everyone is happy. Let's just move on. Now let's discuss tautologies and contradictions. All right. So what is a tautology? I'll just go up a little bit. Yeah. So by definition, we say a tautology is a formula that is always true. All right. What do we mean by formula that is always true? It means you obtain the truth value of true for any assigned truth values to the variables. All right. Another way of describing a tautology, you can say it's a formula that is logically valid. So either you say that formula is a tautology or you say it's logically valid. Now let's see how, if I ask you, for example, in assessment, how do you show me that a formula is a tautology? So let's start with this one. They say show that these two formulas are tautologies. So we have P or not P. Obviously, there's only one variable there. So 2 to the power 1 is just 2. You see, I just have true or false as my two options. Then not P will just be false, true. And if you take P or not P, you see it's true, true. Now, this means it's a tautology. All right. So the way you're going to do is you're going to build a truth table like this. You're going to highlight that whole column to show me that everything there is true. All right. And then your conclusion is that, yes, is this a tautology? Similarly, if we try this one here, again, you have two variables. So you have 4 possible combinations. So 2 trues, 2 false, 1 true, 1 false, 1 true, 1 false. If you do P implies Q, P and P implies Q, P and P implies Q implies Q. Again, look at the outcome here. The outcome here is entirely true. You see, I'm highlighting this whole thing to say, yes, it is a tautology. So all you need to do is to just highlight that whole column that gives you truth value to show that, yes, because everything is true, it is a tautology. All right. Now for a contradiction, I'm sure you can already guess what now contradiction is going to be. It's just the opposite, right? So it's when everything is actually false. So it's a formula that is always false. All right. So no matter what you put in the formula, the output is just false. So we say contradiction is a formula that obtains a truth value, false, for any assignment of truth values. All right. So let's look at this example. We say P and not P. All right. I'm asking a question. Is P and not P a contradiction, a tautology, or neither? All right. So P and not P, notice it. If you do that, you get false and false because the output there, so the outcome they entirely false, we say it's a contradiction. All right. We know already if the outcome were entirely true, it was going to be a tautology. And if the outcome you have a mixture of true or false, then it's neither. So it's not a tautology and it's not a contradiction. All right. So you need to watch out. All right. If everyone is happy with tautology and contradiction, let's move on to logical equivalence. All right. Logical equivalence. You have two formulas that produces the same truth table. All right. When I say the same truth table, it means that if I build a truth table for A, for example, so I'll just go there. So if I build a truth table for A and I build a truth table for B, the outcome, so that last column, which we call the outcome or the output, they should be exactly the same on both sides. All right. Meaning that we call that logical equivalence. Let's look at an example of logical equivalence. This is one here. All right. So you see, I can actually build everything in one table. All right. Everything is done on the same truth table. And how do we prove logical equivalence? If you notice it, you have two variables there. So there's 4 combinations. So just by looking at your truth table, I'll know if you understand the question, if you understand logic at all even. Because some people who've done that in the past, will give them 2 variables. Yeah, they give us 8 combinations. So we assume that that student doesn't know what they actually do. You get a 0. All right. So please read carefully and spend time and just use 2 to the power n every time to make sure they have the right number of combinations. If the number of combinations is wrong, obviously everything is wrong. Now, if you do this, notice it, this, I will call this maybe star, which is the truth value for this. And I'll just call this double star, which is the truth value for this guy here. If you notice it, they're exactly the same. You can see it's false, 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 and a true. Yeah, it's a false, 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 and a true. That's what we call logical equivalence. So star is equals to double star. Therefore, this statement here is logically equivalent to this other statement. All right. This 3 equal sign means logical equivalence. So when they do this, we're talking about logical equivalence. All right. If I use something like this, this is equal to, but immediately I make it 3 means equivalent, means, and in logic, we say logical equivalent. All right. So your left-hand side, which is star, is equal to your right-hand side, which is double star. All right. Since there's no question, I assume that everyone is happy. Now, very, very important. You can see that I say you will be asked in the semester test and exam. So it's definitely a form. This formula say you need to know them. Right? It's a must because you will use them in your semester test and exam. It's a must. You need to know them. And I'm going to explain. De Morgan's law. How does De Morgan's law work? So I need a negation. Remember, this third sign is equivalent to this. All right. So you can either write your not or you can write it like this. All right. So any of this is acceptable as a not. So the negation of A and B. All right. I'll start by having not A. If you negate and, you have or. You can say this an or. And if you negate B, you just have not B. That's De Morgan's law. It applies even when you have or. So you have not A, and then the negation of or is actually and then you have not B. That's De Morgan's law. So this 2 is De Morgan's law. Very important also is this one here. A implies B is equivalent. Remember, I'm using equivalent sign there. If you the key is this equivalent. It means left hand side is always equivalent to right hand side in all of the 6 equations. So left hand side always equivalent to right hand side. We're looking at logical equivalent. So A implies B is equivalent to not A or B. Guys, you need to remember this, right? It's a must. So De Morgan law is important. This third one is also very, 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 very important. And then now if I have to negate this, obviously it will be equivalent to me negating this piece here, right? If I have to negate A implies B, it means I'll just negate not A or B, which just becomes A and not B. All right. So if I say prove that this is equal to this, one way of doing this is start by stating this and then negating the right hand side to actually get here, right? And then 5 and 6, I say learn the proof. There are two ways of doing it. You can use a truth table to actually prove this, that A if and only if B is equivalent to the whole of S. So if you draw a truth table, you notice that for A if and only if B, the outcome will be exactly the same as this on the right hand side. And obviously, if you have to negate A if and only if B, is equivalent to negating this right hand side, right? Go and practice and see if you can actually get this. And to get this, where you see A implies B, you just write it as not A or B. Where you see B implies A, you write it as not B or A, and then negate everything, you notice it, you're going to get this. All right. Practice, practice, practice. The good part is at the end of every logic section, if you look at that note that I uploaded, the compressed original note, it has a lot of questions at the end of every section. So if you can do those, I'm very confident that my test you should be fine. And I have the memos, by the way. So someone that has done everything, they might just be lucky to get the whole memo. All right. But you need to prove that you've actually tried to do those questions. All right. This table is also important. Please go practice. So you have some laws there that you need to remember. Commutativity, associativity, distributive law. You have some identity like A, and a tautology, just giving you A and A or a contradiction. Keep in mind T there in this table stands for tautology and F stands for contradiction. All right, so don't get confused. What does F stands for? So in logic, when you see F, they're talking of a contradiction. And when they put small t, they're talking of a tautology. All right, don't confuse that with capital T. Capital T, we're talking of actual truth value, true. All right, but small t stands for tautology. It means it's a statement that is always true. All right, and I've already discussed the Morgan law. There's also double negation. Obviously, not A is just equivalent to A, right? So not cancels with another not. All right, so if you take double negative of a statement, you just get exactly the same statement. All right, so please look at this table and practice and familiarize yourself. And that also goes with the distributive law, all right? That law there. All right, let's do example 6. Example 6, they say use logical equivalence. So use the logical equivalence above. So we're talking of somewhere on the table to rewrite the following statement in if-then form, all right? And the statement is you get to work on time or you are fired. So it's a very nice one. You get to work on time or you're fired. So the first thing you need to do is assign variables, very important variables. You get to work, you can split this into two. You get to work on time, you can call that P. So P is I get to work on time. And then Q is you are fired. All right. Now, because I say write it in if-then form, I want you guys to always think whenever I use the word if-then form, I'm referring to implication, implies. I'm talking about that sign like that. So this implication means if then, all right. So this statement here, you get to work on time, or it means P or Q, all right. But I don't want you to give me this. This is not what I'm asking you. I want you to give me another version of this, which it has to include this, which is the if-then form. There we go. How do we get it to if-then form? You need to say not P implies Q. It comes back to that exam. If you remember, well, I'm just going to go off quickly. When I say it's very important, I'm sure some of you were doubting why did this guy say that this is important. You remember what I told you guys that this is very important, right? You see, because it is coming back to haunt you. So you need to know this. It's a must. A implies B is equivalent to not A or B. All right. So it means that I can start with a statement that doesn't contain implication at all and move to something that contains implication. All right. So please remember number 3 there. rule number 3. All right. I'm sure some of you are saying, Dachi, how did we get this? I'll just break it step by step. How do we move from here to here? All right. So if you notice it, P or Q, so let me write something on the side. We know that A implies B is logically equivalent to not A, so you negate the first one, and then you say or B. All right. So we all know this, all right? Everyone is happy with this. Now, I've given you P or Q. If you notice it, this guy kind of look like this. So this piece here looks like this piece here, all right? And I'm asking you somehow, I want to see implication. It means you need to work backward now. But because it's a P here and it's not a, you can see it's a P, it's not actually not P. So it means that when you change it to implication, it has to be not P now. All right. I hope that actually makes sense, because if you want to go back, you're going to say not P, and then you're going to say or Q. All right. If everyone is happy, then let's look at example 7. And I'm so sure example 7 is also another exciting one. So example 7, they say write the negation of the following statement. Guys, read carefully, because at every point in time, I'm not testing the same thing. I might be testing something completely different. The first one, I just wanted you to write in if-then form. It means I want to see implication, all right? The next one, I want you to give me the negation of the statement, all right? So they say if Jackie lives in Josh, then she lives in South Africa, all right? So as usual, I split this into 2. P, you can say Jackie lives in Josh. Q, Jackie lives in, okay, so they can say she lives in South Africa. All right. Our original statement is P implies Q. I'm sure everybody is comfortable with that. P implies Q means if then, right? Remember, if I say P implies Q, I'm just saying that if P, then Q. Now I'm asking you for what? I'm asking you for the negation. So your negation, you just need to add your little tilde. If you negate the statement, P implies Q, what do we know about P implies Q? P implies Q is equivalent to not P or Q. You see, logical equivalent. Now, if I negate P implies Q, remember here I'm going to have not P, which will just be P. If you negate or, you have and obviously if you negate Q, you just have not Q. Now you need to write this statement in English. All right, in English, it means Jackie lives in George. You can say it's an and there, and not Q, it will be not in South Africa. So Jackie lives in George and not in South Africa. All right.